Alright guys, welcome to this page of the notes, and again what we're doing is we're taking a look at some word problems, some real world application when it comes to having functions with radicals in them or square roots in them. And the next one we want to look at is this idea relating speed to kinetic energy, right? Now what this tells us, right, the speed v of a ball can be determined by the equation v, velocity, how fast is it going, is equal to the square root of 2 times the kinetic energy divided by m, where kinetic energy and m is, where Ke is kinetic energy, m is the mass of the ball. Now, this should make sense to you guys. Kinetic energy, if you haven't had physics, kinetic energy is just the energy associated with motion, right? You guys are perfectly aware that any object in motion has energy associated with it. It has some sort, it's got kinetic energy. If you've been lucky enough to have been to the ocean and been swimming, one of the reasons we like swimming in the ocean so much is because when the waves are coming in, you stand there firm in the ocean, the wave comes straight at you, right? When the wave hits you, right, you just stand there and nothing happens. No, that's not at all what happens. When you get hit by that wave, which is moving, it has an enormous amount of kinetic energy, and depending on how big the wave is, determines how far you go flying. All right, so you can really easily feel the kinetic energy associated with the movement of that wave. You feel it every time that wave smacks you in the face, right? We have a lot more fun with it when you're on a surfboard or a boogie board or something like that, right? That wave comes along and you get caught up in the kinetic energy of the wave, and it washes you or sends you off to the shore, either on your boogie board or your surfboard. So we know that there's energy associated with moving objects. It also should make sense to you, the more kinetic energy you have, the faster you're going, right? The less kinetic energy you have, the slower you're going. But then it also should make sense to you that mass has to come into it, right? The more massive an object is, the more energy is going to be required to get that object moving, right? So bigger objects require more kinetic energy to move at the same speed as a smaller object, which will require less kinetic energy to go at the same speed. Okay, so it's an inverse relation, meaning the larger the mass, right, the bigger the mass, the smaller the kinetic energy, and the smaller the mass, the larger the kinetic energy. So here we go. We're going to go ahead and do this problem based on the speed of this ball, v, the velocity, just means speed. We're going to graph this function. So here we go. I tell you the mass of the ball is 5 kilograms. Let's write our equation. V is equal to 2 Ke divided by 5. We're taking the square root of that. And again, the reason I plug a 5 in here is because I tell you the mass of the ball is 5 kilograms. Now, we're going to need to set up a table. And here we go. Let's see if we can find some nice, neat numbers to plug in here. My first perfect square is 0, right? So I know that I'm going to want to plug in, oh, hold up, I did it to you again. My domain is kinetic energy. So Ke goes on the independent axis. What depends on the amounts of kinetic energy? Well, how fast the object is going, the velocity, v, which is given to us in meters per second. Kinetic energy, of course, is in joules. So here we go. I plug in a kinetic energy of 0. It should make perfect sense. The object is not moving. 0 kinetic energy. 0 times 2 is 0. Divided by 5 is 0. Square root of 0 is 0. If you have 0 energy of motion, then you're not moving. The next one is going to be a perfect square of, or my next perfect square is 1. So I need to figure out how to get a 1 in here. And actually, it turns out the way to get a 1 in there is to do the opposite of 2/5, which would be 5/2. Right? If I plug 5/2 in here, the 2's are going to cancel, right? This 2 and that 2 will cancel. I'll be left with 5 divided by 5, which is 1. And the square root of 1 is 1. My next perfect square is a 4. So I need to figure out how to get a 4 in here. And I guess the way it's going to work is probably if I plug in a 10. Here's why. 10 multiplied by 2 is 20. 20 divided by 5 is 4, and the square root of 4 is 2. All right, I think that's about all the points I'm going to be able to fit. I know it's only 3 of them, but those are the 3 points that are going to fit on my graph. So let's plot them. 0, 0. 10, 2, that's really easy. 1, and then 5 halves is 2.5. So we'll be at 1. I'm sorry, other way around. 5 halves is 2.5, so we'll go to 2.5 on the x-axis. V is 1. So 1, 2.5, and 1. And I've got myself this real shallow radical function graph, right? It's just real shallow. Okay, so that's what the graph of my function looks like, again, based on the equation that you were given, plugging in a mass of 5 for our ball, and figuring out some values. Let's just jump down here and see what else they've got for us. So here's what we ask you. The ball is traveling at 6 meters per second. What is the ball's kinetic energy in joules? Well, here we go. I could use the equation I was given. V is equal to 2ke over 5, and we take the square root of that. And I want to know, right, how much kinetic energy is needed for a ball traveling at 6 meters per second. So I'm going to plug a 6 in for V and solve. This one was not in our table, so you will need to solve this one for Ke, which we can do. First thing I'll need to do is take and square both sides to get rid of this square root. I got to square both sides, and 6 squared is 36. Okay, next thing I have to do is multiply the 5 to the other side, and 36 times 5 is going to be 180. Divide by 2, 180 divided by 2 is 90. And so for a ball traveling at 6 meters per second, I get it has a kinetic energy of 90 joules. 90 joules. Now, this should make a lot of sense. Let's jump back up here to my graph because this goes a long way to sort of visually give you a representation of something very, very important. To get to 6 meters per second, 1, 2, 3, 4, 5, 6 meters per second, which is not that high on my graph. 6 meters per second actually comes out to about, it's a little over 13 miles per hour. I actually think it's 13 and a half. 13 and a half miles per hour, 6 meters per second. I need to be at 90 joules. Now consider this. Look at how shallow that graph is. Right here's 10 joules. You need to go to 90 joules. That is way, way out there on the x-axis just to get to 6 meters per second, or about 13 and a half miles per hour. And this actually goes a long way to kind of illustrate something really sort of important, and the risk of sounding like a parent. Guys, when it comes to driving a vehicle, all right, you're driving a car with an enormous amount of mass, and think about how fast we drive these vehicles on an interstate where the speed limit is 60, 70, sometimes 80 miles per hour. Now take a look at this graph, right? Look at how shallow that is, right? If 6 meters per second, right, 13 and a half miles per hour requires 90 joules, means your vehicle has 90 joules of motion energy. Just imagine how far out there, how much energy is required to get a vehicle up to 60, 70, or 80 miles per hour. Actually, this gives you a great visual representation of just sort of that analogy they make that a car accident or hitting an object at just 30 miles per hour is about the same as pushing a car off the roof of a 3-story building. Right? You push a car off the roof of a 3-story building and watch it hit the ground. Right? The destruction, you can imagine falling from a 3-story building. That's like hitting an object at just 30 miles per hour. And on the interstate, you're doing 60 or 70 miles per hour. Consider the enormous amount of energy. Now, this is kind of twofold. First of all, it goes to show you that we have come a really long way in car safety between crumple zones and airbags and seat belts, right? The fact that you can get into an accident traveling that fast with that amount of energy and walk away from the accident, or at least walk away from scratches and bruises and maybe a broken bone or two. But really, it actually is kind of staggering that anybody survives an accident, considering that there is that much energy in those vehicles traveling at that speed. And guys, here's what I would say about that. Just please be very, very careful when driving a car. You are driving something that has an enormous amount of energy. Depending on how fast you're going, it can really do a lot of damage. Not just to you, but to those around you. So please be very, very careful when you're driving. The best thing I can say is slow down. And here's a great way of sort of visually showing you what's going on. I mean, you can picture this. If you're driving at 60, 70, 80 miles an hour way up here, just think about how much energy that vehicle has got to have to be going that fast. And when you get in an accident, that energy's got to go somewhere. So please be careful when driving your car. Head on over to the next page of the notes and we'll take a look at graphing radical functions, but the inequality functions. So I'll meet you guys on the next page, and please be careful out there driving.